sense that the state is supposed to be returned precisely, but it's approximate in the sense that there's a time window, or to be more precise, the state's going to be asked for at one point, but Alice doesn't have to return it until some other point that's in the causal future of the first one. So we're going to have a series, Alice is going to be given the state at some start point here, time is going up, and there's going to be a series of call and return points, and if the state is called for at this call point, she's supposed to return it at this return point. It's called here, she's supposed to return it here, and so on. There are important nuances here, so let's try and go through them. We're going to stick with for each call point there's a single return point. There can be many of them in total, but we want there to be a finite number. So n call points and n corresponding return points. In Patrick and Alex's version, Alice knows, according to the rules of the game, the summons will come in at no more than one call point. So if it's called here, it won't also be called here. And then if it's summoned, it's got to return at the corresponding return point. For the moment, I'm not going to worry about what happens if Bob forgets to summon it at all. We'll assume that Alice wins regardless of what she does. So she can return it or not return it anywhere. And there's another point which seems obvious, but actually there is something to say in the case where it's not true. But I'm going to assume that every return point is in the causal future of the call points because it saves fiddly sort of exceptional cases. The fact is you can also comply with the task sometimes when one return point is in the causal past of a call point. And the reason why that's sometimes possible is because you can, if you know you haven't had calls at various other points, you can work out that it must be coming in at this one and so return it in advance of the call. But let's not worry about it. Okay, so our picture is like this. The state comes in here. We have these call and return points set up. Bob is going to say one of these, give me the state back, and Alice is going to say, okay, here you go at the return point. So, there are a couple of very obvious things to say about this version of the task. Obvious reasons why it could be impossible to comply with the task. Well, one of them is if Alice gets the state at some start point here, and she might have to return it at some point that's outside the causal future of the start point. So in that case, she's got an impossible task. She's given an unknown state here, and she's got to propagate it to a space-like separated point, and no signaling precludes that. And the second case is, well, we've already discussed it really with the no summoning theorem. If these two regions, these diamonds, defined by the pairs of call and return points here and here, are space-like separated, then for the argument I gave earlier with Q0 and Q1 applies. Alice can't possibly guarantee to satisfy the task because she would either be violating no signaling or no cloning if she had a strategy that always works in these cases because they're space-like separated. There's also a sort of obvious and therefore not very interesting way in which the task can be easily satisfied. And that's when there's just a path you can send the state along that goes in turn, at least somewhere, through each of these causal diamonds. So if there's a causal path that starts at the start point and hits this diamond somewhere, well, where it hits the diamond, Alice can already know whether or not there was a call. If there was, then she's got the state just here and she can send it along to the return point, and then she's won. If there wasn't, she knows she doesn't have to worry anymore about this diamond, and she could send it further along the path. I'd do the same thing here. If there's a call, she returns it here, otherwise she continues along the path.
Quick question.
Yep.
So far, I think what you've described whether these causal diamonds were just shrunk to points has not been that important. You could have restated these theorems, kind of assuming the call and return things were basically the same thing.
I think that's true, yep.
And
Yeah.
will it end up mattering in the future?
Yeah.
Just want to make sure it hasn't mattered yet and it's going to matter in the future.
It's just about to matter, yeah. So, the surprising to me thing, and I think to many people think, that Patrick and Alex showed, is that if the obvious reasons why it fails don't apply, then there's a way of complying with the task. So the necessary conditions actually turn out to be also sufficient conditions. So here's their theorem. You need two things. Every reveal point has to be in the future light cone of the start point. Well, we already agreed that must be true, otherwise no signaling is violated. And this is another way of saying each pair of no pair of diamonds can be space-like, completely space-like separated regions. So another way of saying that is there has to be a causal path in at least one direction from one of the diamonds to the other. And that's it. If those two things hold, then it's summoning is possible. If you think that's because the whole question is trivial, in this case, that's an incorrect perception. These are surprisingly weak conditions, and I'll give you an example in a minute, but it's, generically, I would say true. They could be satisfied in configurations even when there isn't a trivial way of doing it, even if there's no causal path running from the start point sequentially through all the causal diamonds. So here, and of course that's the interesting case, when it's possible, but it's not obviously possible because you have a straightforward way of just sending the thing along a path. So here's maybe, this is Patrick and Alex's example, or one of the examples from their paper, and maybe the simplest illustration of a non-trivial version of the task. So let's focus on what this diagram is telling us. The call points of y0, y1, y2, and they're supposed, time is going up, and we're effectively thinking in 2 plus 1D because we don't need the third dimension. And you could think of these as all having the same time coordinate. So we've got 3 different spatial points separated by the same distance, equilateral triangle, at the first time. And then we've got 3 return points, all again within a later time coordinate, but all the same time coordinate, also separated by an equilateral triangle, but twisted around. And twisted around so in a precise way, so that there is a light-like path, a straight light ray, going from y2 to z2, and y0 to z0, and y1 to z1. So each call point has a light-like path to its corresponding return point, and so our causal diamonds have they're actually singular in this case. They've sort of squeezed down so that they're just segments of light rays, and there are 3 of them, these black lines.
It would be okay if it had some sort of epsilon width?
It would, yes. But then you've just got an extra parameter, epsilon, so why not?
Sure,
yeah. And the red arrows are also light ray segments. So there's also a light-like path going from every call point to one other return point, and with a cyclic symmetry. So y0 to z2, y2 to z1, y1 to z0. So if you think for a minute, it's clear there's no way of finding a causal path that goes through all 3 of these black lines that are singular diamonds. If you start in, right, even if you start right back at y2, which is your best hope of doing it, you could just about get to the end of that diamond, and you can't get to that diamond at all. So there's certainly nothing we've said so far explains why the task is possible in this case. There's no causal path. There is a like-like path between every pair, though, namely these three arrows.
So if I didn't want to think about 2 + 1 dimensions, I could just make this 1 + 1 dimension, but put it on a circle, the spatial dimension on a circle.
Gosh. What I normally say when people ask the easier variant of that is this doesn't work in 1 + 1D, but you've got a non-trivial topology which you're going to wrap it around.
And then I could just create triangles over.
That's. I don't want to commit in the middle of a talk, but that sounds as though it should work, and that's very nice if true, because in a way it's sort of simpler to think about. In a way, yeah. Thank you.
I was just saying, just take that triangle and then just, I don't want to just
No,
drag
okay.
that so and then use the 1 + 1 dimensions.
Yeah, he was asking, where's the source point? I think the source point is just way down the cell.
Yeah,
It can be way in the past.
the source point could be arbitrarily far in the past, so that won't be a problem. Okay, so for this particular version of the task, there's actually a very nice, simple way of seeing how to comply with it. You start with a secret sharing scheme which takes the unknown quantum state, splits it into 3 states in such a way that any pair of the 3 allows you to extract the original state. So a 2-3 secret sharing scheme. And then you send one of the secrets to each of these points. So you've got lots of time from the source to do that. And now what do you do? Well, if you're, suppose you're at Y2. If you get a call, you know the state's supposed to be at Z2. And the only thing you could do that could be helpful in that regard is sending your share of the secret to Z2. So you do that. If you don't get a call, well, you know the state certainly isn't needed at Z2. And the only other thing you could do that could possibly be helpful to anybody is to send it to Z1. Your share of the secret to Z1. So you do that. So everybody has a clear algorithm. If I'm called, I'll send it to my return point. If I'm not, I'll send it to the only other one I can get to. And if you get one call, say at Y2, then 2 of the 3 secrets will end up at the corresponding return point. So here, the call at Y2 will bring the share from Y2 to Z2. And the call at Y0, the lack of a call at Y0, means the share from Y0 will not go there, but will go to Z2, and so both of those will end up there. And the third one will just be wasted, but it doesn't matter. You've got 2/3 of the thing in the right place, and the state can be reconstructed. So who's familiar with secret sharing, by the way? Or who's not familiar? Oh, no, who's familiar? Most people.
Can you remind me, so secret sharing for any 2 pairs of integers is fine as long as you don't violate no cloning?
Yeah. Yeah, and there's a more general thing which I have a slide about, but it doesn't have to be sort of split up that way. So any sort of access.
Weird pairings that have to happen.
It doesn't even have to be pairings. I mean,
Sure.
any
Combinations.
yeah, you could generate a secret sharing scheme given any set of subsets that are supposed to correspond to secrets, as long as no pair of those subsets is disjoint.
So no coding really tells you everything you need to know, basically, about.
Yeah, which is, I'll say more about that, but yeah, which is beautiful in itself, but also seems to be telling us something about relativistic quantum information. So, that was just a particular example, but why does Hayden-May work in general? You could think about it various ways, and they give a couple of different constructions in their paper already, and there's been more work on efficient construction. But maybe here's one simple way of thinking about it, at least. You've got 2 issues. The first is, suppose you've associated a state, let's call it Cij, with each pair of causal diamonds. So here Ci and Cj and their return points. There's a diamond here and another diamond here. And suppose you know that if there is a call at Ci, you want this thing at least, to go to Ri. And if there's a call at Cj, then you want it to go to Rj. Well, you could do that. And you also know there's a causal path through the diamonds. And so at least one return point has to be in the causal future of the other call points. So the way I've drawn it here, Rj is in the causal future of Ci. So the thing to do then is to take your Sci, start it at Ci. If you get a call at I, you just send it to the return point. If you don't get a call at I, well, you've pre-shared entanglement with Cj, so you teleport it over there, but you don't stick around here with the state. You send on your half of the singlet here to Rj, aware that teleportation might be coming in, and you recombine the signals at or before Rj, and the states return to Rj. So you've got a way of, if you've got a good way of associating states with each pair of calls of diamonds, you've got a way of making sure that those states get to the right return point if a call comes in either diamond. And then the other thing you need is to work out what the Sci should be. Well, and this goes back to Jess's question, as Daniel Gottesman and Adam Smith